Let's discuss a question from machine design. This is from basic static loading. So you have a bolt which is the bolt looks like this. Okay, so you have an axial pull which is of 12 kilonewton and 12 kilonewton, and you have a shear load which is of 6 kilonewton. Okay, so obviously the axial load will induce axial stress, and because it's a tensile load, so it will induce axial tensile stress. So if you take a cross section on the sank, any cross section, so on that cross section, if you look at on that cross section, like if you take a look of this cross section, you have an axial load which creates a tensile stress which is load by area, and load is 12,000 Newton by area. Also the transfer load will create a shear stress which looks like this. Okay, so tau will be the transverse load by area. The area cross section remains same because the same area will be resisting both the tensile as well as the axial. So this is 6,000 by area. So these are the stresses. Now we need to design the bolt. Basically we need to estimate or predict the diameter based on maximum shear stress theory of failure. Now maximum shear stress theory of failure, what does it say is that tau max, the maximum shear stress at a point in a complex loading should be less than or equal to the max shear stress at the time of yield in a uniaxial test. Okay, that's what it says, that's what it predicts. So maximum shear stress from the complex loading is from the given problem we need to find out. It should be less than, but most of the time a factor of safety, it can be equal to the yielding stress, the shear stress at the time of yielding, for failure not to happen. But then what we do is we provide a factor of safety, tau max at the time of the yield by FOS. Okay, now tau max at the time of yield is nothing but, now how is tau max calculated? Because the calculation is general. Tau max is calculated by maximum principal stress minus min principal stress by 2. Now at the time of the yield, okay, let's apply. So this is a general formula to calculate maximum shear stress. Now at the time of yield, the only stress is uniaxial, which is the yield stress. So that becomes the maximum principal stress. Minimum is 0 by 2. So this is my yield maximum shear stress. So and we know the yield stress is given, which is basically 310 MPa. So 310 by 2, which is 155, and okay, so that is your 155. Now how do I calculate the tau max in this problem? In this problem, because you have both the shear stress, so okay, let's substitute tau max is equal to, tau max yield is 155, factor of safety is 2, so this is 77.5. So as per shear stress theory of failure, if the failure shouldn't happen, then your tau max should be, at the most, should be 77.5, considering all the factor of safety. Okay, now tau max, how do we calculate in this complex loading? You have a 2D stress of loading. So we use the Mohr circle concept here, where in general the shear stress is nothing but the radius of the Mohr circle, which is nothing but the maximum principal stress minus minimum principal stress by 2, and by that we have a formula that it's sigma 1 minus sigma 2 by 2. Sigma 1 and sigma 2 are your biaxial. Like if you have an element like this, and this is sigma 2 and this is sigma 1, and you have tau complementary shear stress, then you can apply this formula. Same thing, the given problem is the same thing. If you take an element here there will be sigma and the taus will be always formless. So there is no sigma 2, there is only sigma 1, which is our sigma by 2 whole square plus tau whole square. So this is sigma by 2 whole square plus tau whole square should be a 77.2. Now sigma is 12,000 by 2, that becomes, so let's substitute that here by 2, so that becomes 6,000 whole square by a square plus tau square is also 6,000 whole square by a square is equal to 77. So if I calculate this, I get a as 109 point, and you have to use a calculator, 109.5 mm square. And remember, a is your circular cross section, bolt will have circular cross section, so pi by 4 d square. So from this, d comes out to be 11.8 mm. So that is the answer, 11.8 mm. So this is reasonably good problem. Thank you.